3.7 Implicit Differentiation. Notice that when we take the derivative of x squared with respect to x, we get 2x. But when we take the derivative of y squared with respect to x, we get 2y dy dx. Let me repeat that. Derivative of x squared with respect is 2x. The derivative of y squared with respect to x is 2y dy dx. In a similar manner, the derivative of sine of x is cosine x. The derivative of sine y is cosine y dy dx. This observation is quite useful when we are dealing with a situation where we either can't or do not want to write y as a function of x. For example, consider the circle of radius 1 centered at the origin. This circle is given by the equation x squared plus y squared equals 1. The unit circle, is not a function. Notice that the graph of the unit circle does not pass the vertical line test. We could solve for y and get two functions. One function that would represent the top of the circle and another function that would represent the bottom of the circle. And in that case, if we wanted to find the slope of the line tangent to the graph at 1/2, radical 3 over 2, we would use the first equation, the one for the upper half, and find the derivative dy dx of that function. And just to go through that very quickly, what we would do is we would first rewrite the function, and then taking the derivative, we would have to remember the chain rule, bring down the 1/2, and then I'd have 1 minus x squared to the negative 1/2 times the derivative of what's inside. Then to evaluate, I would use x equals 1/2, and then I'd have some complicated arithmetic to do. The only thing I want to point out is the step after this one. So here I've just done some 1 minus 1/2 squared, that's just equal to 3/4, and 2 times 1/2, that's just equal to 1. The next step you might not be as familiar with. Instead of 3/4 to the negative 1/2, I have 4/3 to the positive 1/2. It's a nice little trick you might want to use someday. I also brought the negative out in front. And then I just finished my cleanup. And if you need to rationalize the denominator, you can do that. All right, so for the point 1/2 radical 3 over 2, the slope of the line tangent to the graph is radical 3 over 3. It can also be written as 1 over radical 3. But that was a lot of work, and there were many possibilities for error. I would like to now show you an easier and faster way of finding dy dx for this problem. This time we will use the equation x squared plus y squared equals 1, and we will not solve for y. So that's one step we don't have to do, is solve for y. Instead, we're going to use this method called implicit differentiation. There are 3 basic steps in using implicit differentiation. You take the derivative, then you get all the dy dx's to the left, and then solve for dy dx. And I will demonstrate doing the exact same problem we did before. So starting with our equation, remember we don't have to solve for y. We just start taking the derivative right away. We take the derivative with respect to x, and I'm going to break the left-hand side up into 2 derivatives. On the right-hand side, the derivative of 1 is 0. Now, taking the derivative, my first term, notice that I'm taking the derivative of x squared with respect to x, so there's a matchup. I'm just going to get 2x. For the second term, I'm taking the derivative of y squared with respect to x. There is not a matchup. I'm going to have to use the chain rule. So, I get 2x for the first term. For the second term, I get 2y dy dx. My next step is to get all the dy dx's to the left-hand side and everything else to the right. So I just subtract 2x from both sides. Last step, solve for dy dx. Going to divide both sides by -2, and this is what I get. You're going to notice that the evaluation is easier as well. Instead of x, I put in 1/2. Instead of y, I put in radical 3 over 2. And I get -1 over radical 3. Now I forgot to rationalize my denominator, but I could rewrite this as radical 3 over 3. Moreover, because we did not solve for y, we did not limit ourselves to the upper or lower half of the circle. And we can use this dy dx, we can use that to find the slope at any point on the graph. If I'm in the lower half, I don't have to use a different function because I didn't use functions, I used the equation. Let's find the slope of the line tangent to the graph, a different graph, at the point 3, 2. So let's just run through the steps again. So those are our 3 steps. The first thing I'm going to do is, with my equation, I'm going to take the derivative of both sides with respect to x. And again, what I'm going to do is notice that the derivative of a constant is 0. On the left-hand side, I have 3 terms, and I'm going to take the derivative of each of those terms. So I have 3 derivatives to do. The first derivative is fairly straightforward. The second derivative causes me a little bit of confusion. The second derivative is the derivative of xy. Now x times y is a product, so I have to use the product rule. So I'm taking the derivative of a product. So the derivative of the first times the second plus the first times the derivative of the second. The derivative of x with respect to x is just 1. The derivative of y with respect to x is also just 1. But now we have to add the chain rule, dy dx, because the variables don't match up. The third derivative is, at this point, fairly straightforward for us. Notice that the letters don't match up, so I'm taking the derivative of y to the 3 with respect to x, getting 3y squared dy dx. Once I've taken all my derivatives, I'm ready for step 2. Get all the dy dx's to the left-hand side, everybody else to the right. After I do that, step 3 is to solve for dy dx. To solve for dy dx, I'm going to factor dy dx out of these 2 terms over on the left-hand side. So the left-hand side has dy dx in both terms. Factor that out. What will I get? And once I do that, I divide both sides by x squared minus 3y squared, and I get this quotient. Alright, now once I've done this, I can go ahead and evaluate. Instead of the 3, instead of the x, I'm going to put in 3. Instead of the y, I'm going to put in 2. Once I do that, I'm all done. Alright, just one more example before I leave you. Let's go back to the unit circle, and this time let's find the second derivative. Recall that we have already found the first derivative, so we'll start there. Take the derivative of the first derivative, and on the left-hand side, That's just going to be the second derivative. But on the right-hand side, I have to use the quotient rule. So set up the quotient rule, and just a reminder, on the left-hand side, when I take that derivative, that's just the second derivative. That's what that means. All right, so once I set up the quotient rule, go ahead and take those derivatives. Again, the derivative of negative x is negative 1, and the derivative of y is just dy dx. Wait a minute, now this is very interesting. Dy dx, we know what that is. Dy dx is equal to negative x over y. So instead of dy dx, let's put in negative x over y. Now that looks a little bit better, but we certainly have some more cleanup to do. What I suggest we do is we multiply the top and the bottom by y. So it will look like this. When we multiply the top and the bottom by y, we have to be very careful in the numerator. We're going to have to distribute that y. All right. So for my first multiplication, I'll have negative 1 times y, and that gives me negative y squared. For my second multiplication, I'll have negative x times negative x over y times y, and that gives me x squared. Pull out the negative x, and wait a minute, we have another observation. X squared plus y squared equals 1. Remember, that was our original equation. So instead of the y squared plus x squared, I'll just put in 1 and get this beautiful little formula for the second derivative of negative 1 over y to the 3. For more examples, I suggest you look at the Ask My Instructor videos that I have for this section. Take care. Let me know if you have any questions. Have a great day.